is the seventh lecture on the theory of small oscillation. In the last class, we have considered an example of two coupled oscillators where the 2 point masses were connected by three horizontal springs, three horizontal elastic springs. Today, we shall consider another system of two coupled oscillators. There are two coiled oscillators, identical oscillators, each comprising of a bob of mass m is hung from a rigid support by an inextensible string of length L. And if there were no string, each pendulum could execute simple harmonic motion. But here the two bobs are connected by an elastic spring of spring constant K. Our aim is to solve the problem by using the theory of small oscillation. Towards this, we first admit that this system has 2 degrees of freedom and θ1 and θ2, that the angle that the oscillators makes with the horizontal vertical direction are treated as the generalized coordinates. And the kinetic energy of the system is the sum of kinetic energy, so half ml square θ1 dot square plus θ2 dot square, which leads us to the kinetic energy matrix ml square 1 0 0 1. Since there is the off diagonal terms are 0, there is no coupling in the kinetic energy term, that is, there is no inertial coupling. I will come to this point later. Now the potential energy. The potential energy has two parts. One is the gravitational potential part, gravitational PE, plus the spring potential energy or elastic potential energy. If we consider this is the zero level of the system, this is the zero level, then this bob is at a height, this is mgl 1 minus cos theta 1. So L into 1 minus cos theta 1 is this much, this height, this extent. So this is the, and for the mass 2 it is mgl 1 minus cos theta 2. And for the gravity and the elastic potential energy is half k into the compression or rarefication, which is L square theta 1 minus theta 2 whole square. This is the elongation. L theta 1 difference theta 2 is the elongation or change in length of the spring from its equilibrium position. So this is the potential energy. If we expand in the limit of small amplitude oscillation, this is mgl, and 1 minus cos theta is theta 1 square by 2, and similarly for this mgl theta 2 square by 2, where we have expanded cos theta as 1 plus theta, 1 minus theta square by factorial 2, so this is theta, so this 1 cancels with this and this minus and makes it plus. Then coming to this part, this is half kl square theta 1 square plus theta 2 square minus twice theta 1 theta 2. This can be written as, note that in the kinetic energy part there is a common term taken out ml square. So with this spirit we write it as ml square taken common. So first term as this is G by L and this is K by M. G by L plus K by M. There is a contribution of theta 1 and there is half factor also. Theta 1 square plus theta 2 square. And coming to the cross term is K by M twice theta 1, theta 2. So if we go for the matrix for V, the V matrix is half part is not there, so this is ML square G by L K by M, this is one term. This is minus K by M, this is also minus K by M, and this is G by L plus K by M. This is the V matrix. So the V matrix coming to the this is the V matrix. Now, our aim is to find out the eigenfrequencies. The eigenfrequencies are obtained from the secular equation. Before going to that, this is V matrix. You see that there are off-diagonal terms present in the V matrix. So the coupling is through the potential energy. Such coupling is generally referred to as stiffness coupling. Now we want to find out the eigenfrequencies. Eigenfrequencies are obtained from this V minus omega square t det is equal to 0, which in this case, since we have ML square common, we need not to consider this. So the corresponding determinant is G by L plus K by M minus omega square, and for this it is minus K by M minus K by M. This is G by L K by M minus omega square. This is equal to 0, which gives us G by L plus K by M minus omega square is equal to plus minus K by M. If we evaluate the determinant. So omega square is equal to G by L plus K by M plus minus K by M. So this is either G by L or G by L plus 2K by M. We call this as omega 1 and this as omega 2. Sorry, omega 1 square and omega 2 square. So the eigenfrequencies are omega 1 square is equal to G by L and omega 2 square is G by L plus 2K upon M. Now the eigenvectors, coming to the eigenvectors. Eigenvectors are obtained by solving this equation, that is G by L plus K by M minus omega I square minus K by M minus K by M G by L K by M minus omega I square, this matrix when multiplied by the A1I, A2I is equal to 0. This is the circular equation. For omega is equal to omega 1, for omega square is equal to omega 1 square is equal to G by L. We see that this cancels and we have K by, this is plus K by M, this is minus K by M, this is minus K by M, this is plus K by M. So taking K by M common, this is 1 minus 1 minus 1 1 A1 1 A2 1 is equal to 0. This leads us to the fact that which gives us A1 1 minus A2 1 is equal to 0, or A11 is equal to A21 is equal to alpha set. How to determine alpha? Alpha is determined from the condition that to determine alpha we use the normalization condition of T matrix. This is summation over Ij AI1 Tij Aj1 is equal to 1. Since the T matrix is diagonal, this becomes A11 square T11 plus A21 square T22 is equal to 1. Since this is alpha, this is also alpha, so we have, and T11 is simply ml square. So twice ml square alpha square is equal to 1, or alpha is equal to 1 upon 2 ml square square root. So the first eigenvector A1, or in terms of ket, it is a column matrix A11, A21. If we take alpha common, this is 1, and in the compact form, this is 2ml square root 1 1. So this is, and if we put the second root minus g, this one, then this will cancel this and it will make this one as minus k by m, in which case we will see that the sign will be plus, and the second eigenvector A2 would be following the similar procedure, we get 1 minus 1. This is the A2. So the eigenvectors are A1, and eigenvector 2 is A2, one minus 1. What does it mean? What is the physical meaning of this? Let me first explain this one, and then I will go for the other things to be determined. First one, it says that both the oscillators moves in the same direction. If the oscillator 1 moves towards the right, the 2 also moves towards the right. If 1 moves to the left, 2 also moves to the left. So undisturbed position equal equilibrium position, and this is displaced position. The equilibrium position is that it is the position of particle 1 and this is particle 2. Displaced position means it has moved to this point. Similarly, this one has moved to there. So both of them are moving either towards the right or towards the left. So these are the two displaced positions for omega is equal to omega 1 is equal to g by L square. So this motion is called in-phase oscillation. This is in-phase oscillation. And for this one, we see that the displaced position is, say the oscillator 1 moves towards the right and the oscillator 2 moves towards the left. Or we may have situation the oscillator 1 moves towards the left, in that case oscillator 2 moves towards the right. So they are 180 degree away. This is for omega is equal to omega 2 is equal to g by L plus 2k by m. This represents out of phase oscillation. Out of phase oscillation. This is out of phase oscillation. Now the next part is to find out the modulus of the amplitudes. The amplitudes eta 1 and eta 2. So this is in phase oscillation, this is out of phase oscillation. Now we come to the eigenvectors. Eigenvector, we define eta 1 as a function of t as summation over eta I. We define eta I as a function of t is summation over k is equal to 1 to n a ki e to the power I omega kt plus phi k, and which we write alternatively as summation over k a ki some constant ck e to the power I omega kt. So in this spirit, eta 1 of t is equal to a11 c1 e to the power I omega 1 t plus a21 c2 e to the power I omega 2 t. If we use the value of a11 and a12, this is 1 upon 2ml square. Then we have c1 e to the power I omega 1 t plus c2 e to the power I omega 2 t. And similarly, eta 2 as a function of t is 1 to c1 e to the power I omega 1 t plus a22 c2 e to the power I omega 2 t. And for This A12 is this and A22 is this. So we have 1 upon 2ml square C1 to the power I omega 1t minus C2 e to the power I omega 2t. Now the modal matrix, coming to modal matrix. This is matrix A is A11, A12, A21, A22. This column is coming from eigenvector A1, this is from eigenvector A2, which is 1 upon 2ml square, 1, 1 minus 1. So, det of A is 1 upon 2ml square and minus 2. So minus 1 upon ml square. We then form the matrix of cofactor matrix. Cofactor matrix, it is minus 1. For this element, if we suppress this, this is 1, but minus 1, then this is minus 1, this is plus 1. And if we consider the transpose of it, it is its transpose. So this is also AC transpose, and A inverse is 1 upon det A times AC transpose. So we have 1 upon 2ml square root. Then det A is a minus sign that I will adjust with these elements, and this is ml square in the top. And this each element will change its sign. So ultimately this is ml square by 2, 1, 1, 1 minus 1. So the modal matrix is this, and A inverse is ml square by 2, 1, 1, 1 minus 1. Now coming to normal coordinates. Normal coordinates is defined by the fact that get eta is equal to modal matrix times J. So this is the normal coordinate, so which gives us that J is equal to A inverse eta. That is to say J1 is, apart from this factor, ml square by 2. This is eta 1 plus eta 2. And Xi2 is ml square by 2 eta 1 minus eta 2. If we put the value of eta 1 and eta 2 over there, we get ml square by 2 is coming from here, and both eta 1 and eta 2 has a factor of 1 upon 2 root ml square. Then for eta 1, it is C1 to the power I omega 1t plus C2 to the power I omega omega 2t. This is for eta 1 plus c1 e to the power I omega 1t minus c2 e to the power I omega 2t. This is for eta 2. This is eta 1 eigenvector. This is eta 2. So we see that this part cancels and this is twice, which adjust with this. So we get xi 1 as a function of t c1 e to the power I omega 1t. Similarly, if we write for xi 2, this part is simply half as in this case. Then we have c1 e to the power I omega 1t plus c2 e to the power I omega 2t. This is for eta 1, then minus c1 e to the power I omega 1t minus c2 e to the power I omega 2t. So this part cancels and this part survives, and we get xi 2 of t is equal to c2 e to the power I omega 2t. This is the normal coordinates. So we have solved two problems of small oscillations extensively. There are similar examples which I shall not go to evaluate exactly, but we shall, or in detail, but we shall just outline the things that has to be done. So we consider the third application. As the third example, we consider again a system comprising of two masses. I am confining myself to systems having 2 degrees of freedom, and they are connected by two vertical springs. So, two masses connected by two vertical springs. So the situation is something like that. We have a rigid support. There we have an elastic spring and a mass m1 is connected with it. And there is another spring of spring constant K2 and second mass m2 is hanged from this. And the entire system can move vertically up or down. So the kinetic energy is as usual. The kinetic energy is half m1 x1 dot square plus half m2 x2 dot square. So the kinetic energy operator P is m1 0 m2. And the potential energy of the system. The potential energy will have two parts. One is this spring. This is half k1 x1 square, the potential energy of this spring. And for this spring, the potential energy or the elongation is the dependent on this relative displacement of 2. So this is the displacement. So which can be written as half k1 plus k2 x1 square plus half k2 x2 square minus k2 x1 x2. So the matrix for the potential energy is k1 plus k2. This is minus k2 and this is k2. This is the potential matrix for potential energy. Recall that this V is written as half x1, x2, V11, V12, V21, V22 times x1, x2. So which leads to this matrix form. And the other things, the eigenfrequencies and other things can be obtained very easily. To simplify the situation, for M1 is equal to M2 is equal to M, and K1 is equal to K2 is equal to K, we have the eigenfrequency omega 1 square is equal to three plus root 5 2m, and omega 2 square is k 3 minus root 5 upon 2m. As it is apparent from the very expression that the eigenfrequencies are has a complicated manner. Alright, this is the application 3. The eigenfrequencies are already complicated, so the next calculation will involve a bit algebraic complication, but the procedure is same. This is left for you to be worked out. Now coming to the fourth application of a two-dimensional system. It is a simple pendulum comprising of a bulb of mass small m and suspended from a string of length L as usual, but the point of suspension is connected by two horizontal springs. That is the point of suspension of a linear harmonic oscillator is connected by two horizontal springs. Obviously, elastic springs. The situation is something like that. We have two rigid supports. There is a spring of spring constant K. We have a body of mass M situated over here, and it is connected by another spring. This spring constant is K1, K2, and a simple pendulum of length L and mass M is hung from this. So this point executes simple harmonic motion under the action of these two springs, and this part, this one executes as usual planar motion. The kinetic energy operated is half m. This is, if we call this x dot square, it is the displacement along this is x, and generalized coordinate is assigned to it is x, and for this it is theta. So it is half m square theta dot square. So the kinetic energy operator is simply m0 small m. Sorry, ml square. This is the kinetic energy operator. And potential energy, the potential energy of this spring is half K1 plus K2 excess square, because there we have two springs, so this is half K1 K2 square, plus if we consider this to be the zero level, then this energy is mgl1 minus cos theta which can be approximated to x square. This is half mgl theta square. So the potential matrix is K1, K2, and this is this is 0, 0, mgl. One thing to notice that although we have developed the theory for coupled oscillator, but these two oscillators, so to say, are not at all coupled. There is no inertial coupling since the P matrix is diagonal. There is no stiffness coupling since the P matrix is diagonal. So in that sense, this is not a problem of coupled oscillations. So we can still work it out, and we shall find that one eigenfrequency will be the frequency of this pair simple oscillation of this ball, that is G by L form, and it will have a eigenfrequency omega say 2, this is K1, K2 by capital M. So these are few problems on small oscillations of 2D system. In the next class, we shall first take up the situation when the Lagrangian is supplied, and we are to identify the kinetic and potential energy part, and then to construct the theory for simple harmonic oscillation.